So this is a different kind of talk in a sense that it's not really going to be talking about very recent research. The idea of this talk actually came from an invitation I got to talk a few months ago at Purdue University in Indiana, in the U.S. So they invited me to come give a talk, and then they suggested, well, you know, people learn about these interactive proofs in classes, but they don't really know the kind of story that goes behind it. And they were wondering, well, could you tell a story? Could you tell us, you know, how all these things developed? I said, yeah, it's kind of interesting, especially from a perspective more than 30 years later. You know, and most of what I'm going to be talking about happened before most of you were born. So it's interesting. So I think it's kind of, it was interesting to see how it all developed. You know, particularly, how did we get to this? This was an article that was in the October 1993 issue of Scientific American called The Death of Proof. So what led us up in the years before that to actually get to someone claiming that proofs were dead? And so to do that, I'm going to go back, you know, sort of, I'm going to kind of give this history of interactive proofs. I'm kind of give it, you know, it's just one of many, many players in this field. But I want to kind of give it from my point of view. You know, just how did I see it develop? Because I really did have a front row seat to this. And it was, and so, and in order just to make the story kind of personal, how does it develop for me? And develops for me, it starts when I started grad school. I started grad school at the University of California at Berkeley. And some of you might think, well, didn't you just say I graduated from MIT? So there's a story there too. But I did start grad school actually as a PhD student at Berkeley in the fall of 1985. So let me see what happened. So I went to grad school. I was trying to figure out what should I do research in. Actually, I figured out who my advisor should be pretty quickly. Mike Sipser, who was one of the best probably the best known complexity theorist at the time in the mid 80s. A lot for his work on circuit complexity. So what Mike did was, Mike suggested, and I still do this with my own students, he said he gave me a copy of a recent STOCK proceedings. So STOCK is a theoretical computer science conference, and back then proceedings actually came in a book. So actually giving me a physical copy of the book with all the papers in it. And he said, go read this book and try to find some paper that interests you, and come back and talk to me about that paper. So I went to the book and I came up with this paper, A Model Theoretic Analysis of Knowledge by Fagan, Halpern, and Verdi. Oh, this is a wonderful article about the muddy children's problem and how do you know that all, you know, like one of those problems where some number of kids all the kids have muddy foreheads, but how does anyone know that their particular forehead is muddy? You've seen games like this. So I get all excited, I read this paper, I find it really interesting, I go to talk to Mike about it, and Mike says, you know, if you're really interested in knowledge, don't read this paper. Read this paper instead. The Knowledge Complexity of Interactive Proof Systems. And I got to say, these two papers have nothing in common except the word knowledge in the title. But that's how I got involved in interactive proof systems. So instead, I know, listening as a good student, it would have been really different if I had a different advisor. I went and read this, and this is actually a pretty fascinating paper in itself. Although a lot of, you know, the initial versions of the papers had a lot of issues, but still it became an interesting paper. And more importantly, this paper became, it wasn't so much the paper itself, but the definitions and what would happen with the models that were defined in this paper. So the knowledge complexity, so this is a paper by Shafi Gowas, Sylvia McCauley, and Charlie Rakoff. It came from the cryptographic community. The question is, you know, much the way differential privacy is now trying to come up with the right definitions of privacy and how do you apply them, and making progress there. Knowledge complexity of interactive proof systems was trying to capture a formal notion of knowledge. What does it mean for a protocol to leak information? How do you define something where a protocol does not actually provide any information beyond what it's trying to actually achieve? And because they figured if they could formalize this, then maybe they can then prove theorems about it and then analyze it and study it, much the way you're starting to see today with differential privacy. So, so let me try to, and to kind of give you an idea of interactive proof systems, I'm going to tell you a real life story. So one day I was shopping with my wife, and she holds up 2 shirts, and she says, "Which shirt do you like better?" Now I'm this is a true story. These aren't the real shirts, but I'm colorblind. And being colorblind, the shirts looked identical to me. So that she holds up 2 shirts. They look completely identical to me, and she says, "Which you like better?" I said, "Listen, they look the same to me. I'm colorblind. They look the same to me. I think you're just trying to trick me and make me feel weird that you're claiming these 2 shirts are different. I mean, they just look the same. I'm sure they're the same shirt. So how can my wife convince me that these 2 shirts are actually different?" And what we did was we got a trusted third party. She got someone who worked at the store who said that we brought her over and said, "Are these shirts the same or different?" She said different, and okay, I accepted it. But how could we have done it without a trusted third party? So, and if you've seen this if you know much about interactive proofs, does anyone see how to do this? Without a trusted third party, my wife could convince me these shirts are different, even though there's no way by looking at them I can tell that they're different. Color filter. That would be the physical approach. But assuming that there's actually so that's exactly the right idea. The idea is I take both shirts, I somehow keep track of them behind my back, I swap them around, I show her a random shirt and tell her which would they start with, 1 or 2. And if my wife gets that right, well, she might have gotten lucky, so I do it again. I do it like 10 times in a row. She's always getting it right. Then I should have some strong confidence. It's not going to be a proof that's going to be 100% confidence. Strong confidence that the shirts are actually different. So, so this Goldwasser and Macaulay-Rakoff paper, try to formalize this idea of the interesting thing is that they talked about knowledge, but the first definition actually was just about what's an interactive proof. What does it mean to prove something? And they changed the notion of proof. Instead of proving something by just me giving you like NP, like if I want to prove to you a formula is satisfiable, I give you a satisfying assignment. This is something where there's conversation back and forth. And you have some extremely powerful prover. In this case, we'll use Merlin. We have some computationally limited verifier, say Arthur. And they have a protocol back and forth, but Arthur also has access to some random coins that Merlin can't see, although we'll get to that later. And they have back and forth questions, and then eventually Arthur will say he's convinced or not convinced. And then, but the definition basically goes is that if the proof is legitimate, then Arthur should be convinced by probability. And if the proof is not legitimate, then Merlin, no matter how he tries to cheat or change or whatever he says, he should not be able to convince the Arthur of what he's doing. So the randomness here, for example, is I had to randomize the shirts behind my back. The name actually Arthur and Merlin comes from another paper by Laszlo Babai and Shlomo Moran. Arthur Merlin games, the randomized proof system hierarchy of complexity classes. They actually came up with this effectively the same model with some variations, but effectively be an equivalent model for a different reason. You know, Goldwasser, Macaulay, and Rakoff came to it via cryptography. Bob and Moran came to it out of group theory. They had some group theory questions they tried to characterize. They couldn't figure out how to characterize them using traditional NP, traditional I give you a proof. They found some randomized way to do it, and they called them Arthur Merlin games. So the name Arthur Merlin came from this paper of Bob and Moran, and now these days we actually say that interactive proofs were developed independently, because essentially they were, by these two papers. And the interesting thing is they both came from very different applications, one from the cryptography application, one from the trying to understand group theory problems applications. What did I press? Okay. So let's move on tonight. So that kind of those kinds of papers came out 84, 85, and 85 is when I came into it. But you know, these were still kind of like, okay, so we added some randomness to NP. What's the big deal? Didn't seem to actually bias much, but that's the big change happened in 86. So the first thing is this Goldwasser-Sipser results. I mean, sort of all of a sudden we started getting some surprising results. So Goldwasser and my advisor Mike Sipser, they showed that public versus private coins were the same. So what does that mean? Well, private coins is where I flip coins and you can't see them. You know, like when I swap the shirts behind my back and you don't know how I randomized the shirts. Public coins means that when Arthur flips the coins, he flips the coins in front of Merlin. Just flips them in front of Merlin so Merlin can see the coin flips. That would ruin my protocol, because if my wife knew how I randomized the shirts, she could cheat every time. So at least computationally, I don't know how to do this for the shirt problem, but at least computationally, Goldwasser-Sipser showed it didn't matter. It's kind of a surprising result. It didn't matter. Take any protocol where you could have the private coins, you could convert it to a different protocol which had public coins, and it would be it would still work. I mean, it wouldn't necessarily be the same protocol, but you could convert the protocol to a different protocol. And that was the first kind of one of many surprising results. But that wasn't as earth-shattering as I think this result. Goldreich, Macaulay, and Wigderson. How to prove all NP statements in zero knowledge and the methodology of cryptographic protocol design. So what did this paper do? This paper showed that I could take any problem in NP. So what's NP? NP is, does anyone here not know what NP? I shouldn't say that because then I'll embarrass you. But NP is, you know, the P and NP problem most of you have probably heard of. All of you should have heard of. NP is basically a set of things I can kind of prove to you in the old traditional way, like convincing you that a formula is satisfiable, a graph is to be colorable, that kind of thing. And this says you can take any NP statement, and I can convince you that it's true without in what's known as zero knowledge. What's zero knowledge? Zero knowledge is the only thing you learn is that the statement is true, is that the formula is satisfiable, is that the graph is to be colorable, and you don't learn anything about the coloring or the assignments or anything like that. And this is important. Now, I found this important actually because I had just in the fall of 85 taken a class by Manuel Blum. So again, I'm giving my perspective of this. In the fall of 85, I took a class with Manuel Blum on cryptography. Manuel Blum is he's famous for doing lots of different things. But he's a Turing Award winner, and he was also the advisor of both Shafi Goldwasser and Sylvia Macaulay and Mike Sipser. So lots of other well-known people. So in that fall course, Manuel Blum, he spent like half the class going over various protocols for doing things like, here's a number, how do I convince you that it's the product of three primes without revealing what the primes are? And he would just he spent a lot of the class doing those kinds of things. How do you create protocols that convince you of something without revealing information? And then this paper came out 6 months later and basically wiped that all into one general result. So this one general result completely changed the way, at least in theory, how you do cryptography. It just made a lot of things all of a sudden very simple. It's quite the theorem. So I'm not going to do a lot of proofs. In fact, I'm barely going to do any proofs at all. I'm not going to prove this formally. But I want to kind of give you how this flavor works. And I love to do this example for Sudoku. So the idea is that Bob is working on a Sudoku puzzle. And Bob wants to give up. Bob is saying, I can't figure this out. I can't figure out the Sudoku problem. I don't think there's a solution to this problem. I think there's a mistake in the problem. It can't be solved. But Alice has already solved the Sudoku puzzle. So Alice knows there's a solution. Look, there's a solution to the puzzle. Now Alice could just show Bob the solution and say, look, Bob, you're wrong. Here's the solved puzzle. But then that would ruin the puzzle for Bob. Because once Bob saw the solution, Bob would say, okay, well, I'm not going to solve it anymore. I've already seen the solution. It's no longer fun to me. So is there a way for Alice to convince Bob that the solution exists without revealing the solution? So Bob knows the solution exists. So Bob will stop thinking that no solution exists. Bob's going to be convinced the solution exists. But we're not going to reveal any information to Bob, so Bob could still try to work and solve the problem on his own. So let me show you how we do that, because it's kind of sort of not complicated, and it really does capture the proof of Goldreich, Macaulay, and Richardson. So what does Alice do? Alice has to do some preparation work. Alice takes the puzzle, picks a random permutation of the numbers. So consider this a random permutation, and then permutes all the numbers in the puzzle. So you take the 1 here, you look it up in the table, 2, the 9 becomes a 3, etc. You just apply this random permutation to every element in the puzzle. So this is our permuted puzzle. It's the same answers, just in a permuted order. And then you put each of the numbers into a little pouch. And all the pouches look identical. So from the pouches, you can't tell what number is which. And then you ship, and then you take all these you take the puzzle with all the pouches on it, and you put it on the table. And then you say to Bob, Bob, you have a choice. You can either choose a row, you can choose a column, you could choose a 3x3 square, and I'll open up those pouches. So for example, if you pick the row, Bob will open up all the pouches in this row. Bob gets to open up all the pouches in a row, and Bob sees, what does Bob see? Bob sees all the numbers 1 through 9. They should all be different, but if you think about it, since Alice randomized the numbers, it's just going to be a random permutation. And the same would happen if Bob were to look at any column or any 3x3. Now this doesn't, Alice could still cheat because maybe this wasn't connected to the real puzzle. So to get around that, there's one other possibility. Bob also gets to say, show me the original puzzle. So by that, Alice opens the numbers corresponding to the numbered part of the puzzle, and Alice, in that case, gives the permutation, and Bob could see that if you apply the permutation backwards, so 3 became 9, then, and if you check, this was the original puzzle that we started off with. So Bob basically has 28 choices. One of the rows, one of the columns, one of the boxes. That's 9 plus 9 plus 9 is 27, plus this 1 where you open up the whole puzzle. Now Alice could easily cheat. Alice can make one row look good, and everything else can make most of the rows and columns look good with maybe changing one number. So this only gives, if Alice tries to cheat, this only, if all these things were true, if all the rows were accurate, if all the columns were accurate, and this thing corresponded to a legitimate puzzle, that could only happen if Alice didn't cheat, if Alice really had a solution to the puzzle. And but given all that information would reveal the puzzle. So the point is that if you do this, Bob has a 1 in 28 chance of capturing Alice if Alice is cheating. That's not very high, so you have to repeat this process. Now, repeating the process is not easy. Alice has to re-randomize and start from scratch with new pouches. But if you repeat the process, say 50 times, 100 times, it's going to be very unlikely for Alice to always convince Bob that Bob is correct. Convince that if there really wasn't a solution, Alice would not be able to convince Bob. And so that's how this kind of zero knowledge proof for Sudoku goes. Sudoku is basically, if you think about it carefully, it's just a coloring problem. And that was the original solution, was trying to color. So, for example, can you color, so map coloring is an example. I mean, you can do this with 4 colors. And then once you have an NP-complete problem, like graph coloring, you can apply it to any other problem by reducing it to graph coloring and then do the zero knowledge protocol for that. So traveling salesman you can do. And then I also want to mention this case, so traveling salesman or satisfiability or any other of the thousands of NP-complete problems that are out there, you can convince someone in zero knowledge. And let me mention one other problem that's out there. This is graph isomorphism. Graph isomorphism is a protocol that graph isomorphism is a protocol that is a problem where you want to say, can I take these 2 graphs and can I, are these basically the same graphs? If I were to move all the nodes from one place to another, would these 2 graphs, is there some way to move the nodes on the left or corresponding nodes on the left to the nodes on the right such that these 2 are exactly the same graphs? And the answer is yes. I'll let you try to figure out how to do that, that these 2 are in fact the same graphs. And the interesting thing is that the other result in the Go-Reich-Macaulay-Widgerson paper is not only that there's a zero knowledge proof for graph isomorphism, in fact there's an interactive proof for graph non-isomorphism. I can convince you, if these graphs were not isomorphic, I could actually convince you they're non-isomorphic, even though there's no corresponding there's no way to give you a there's no way I can convince you 2 graphs are not isomorphic, even though it's not known to be an NP. So there's no NP algorithm. There's no proof, sort of proof I can shortly write down that proves 2 graphs are different. That's still open. But there is a way if you ask me random questions, and basically the protocol is just the same as that kind of shirt protocol. You randomize you just take a random permutation of one of the graphs, and you see if Merlin can tell you which graph you started with. And that's basically the protocol for convincing you that 2 things are different, even though you can't tell whether or not they're different. So now 1987. And 1987 is sort of where I start to get into the picture. So this is my first major conference paper, The Complexity of Perfect Zero Knowledge. And what did I do? Well, if you look at the zero knowledge protocol for say, Sudoku, never put all these numbers in the bags. And, in computer science, we don't actually use bags. To get the concept of bags, it's sort of what's called bit commitment. And it uses cryptographic processes. These bags really that you create don't all look the same. I mean, they all look it's not that they all look the same. They don't all look the same. The point is that you can't computationally tell the difference. So a bag containing 2 versus a bag containing 3, they'll have distributions. I mean, there's some randomness involved. You create distributions for bags containing 2 and 3, and those distributions, they're not going to be the same distribution, but computationally you can't tell the distributions from each other. That's a critical part of the Sudoku protocol. But if you looked at the isomorphism question, this is interesting. If you look at graph isomorphism, the zero-knowledge protocol for showing things are isomorphic. That's actually different. You can actually do that without cryptography, without having to hide information. You can just, there's just a way to do zero knowledge for graph isomorphism where you don't need to actually hide the information cryptographically. And then there was a question, in the wrong direction, for zero knowledge, for NP problems, do you need to do the cryptography? Do you need to hide the information? Or is there some way you can have an information theoretic protocol? One where these bags really have the same distribution, no matter where they came from. And the answer is no. That was my big first theorem. No, in a sense that if you could do zero knowledge for general NP problems, and you could do it in kind of this information way, something I called perfect zero knowledge, what would later be called, probably better name, statistical zero knowledge, then bad things happen. Polynomial hierarchy collapses. You don't need to know what that means, but this just seems unlikely. So that's sort of how I got into the field. My thesis was called, so I did my thesis in interactive proofs. My thesis was called the theoretical aspects, the complexity theoretical aspects of interactive proof systems. So I was really into it at the time, even though I'm going to later see my best work on interactive proofs came after my PhD. So in 1988, there was a way. They did come up with, this is Michael Ben-Or, Shafi Goldwasser, Joe Killian, who was a grad student with me at MIT, and Avi Wigderson. Avi became like the sort of the complexity leader after Mike Sipser. It was Sipser, then Avi became kind of the head, and he was basically on almost every important paper in complexity at some point. They actually came a way to get rid of the cryptography to do zero knowledge, but they had to change the model to do it. And the way they changed the model is, here's the kind of traditional interactive proof systems. What if you had multiple provers? So what's multiple provers? Multiple provers is you have, basically what it's like, you have multiple Merlins. Arthur can ask questions to the different Merlins, and Merlins could give answers back to Arthur. Now the important thing is that the two Merlins cannot communicate. So there's no communication possible between the Merlins. Merlin cannot see the conversation Arthur had with one Merlin versus the other. Now, why would this might be more interesting or more powerful? And the way to think about it is, what if suppose you have two suspects in a crime, and you want to interrogate them? Do you put them in the same room, or do you put them in different rooms? And the police will generally put them in different rooms. Why? Because you can ask questions to one suspect and ask questions to the other suspect and see if their stories are the same. Because if their stories are different, that means that at least one of them is lying. So this is kind of interesting. They're trying to give a proof that they're innocent. And they'll be much more convincing that the proof is innocent is if you put them in different rooms. So the police actually being good to the suspects by putting them in different rooms because it's more likely to convince the police that they're innocent, I like to think. So that's kind of the theory, and in fact it does lead, for example, they showed in that paper, Ben-Or, Goldwasser, Killian, Wigderson, BTKW, that you can do zero knowledge proofs without cryptography by having these multiple provers. Now that was kind of interesting. But the reality is it turns out this multi-prover model turned out to be a very important model. And so then Mike suggested we looked at this. So I looked at this with another student, John Rompel. And we looked at this multi-prover interactive, this multi-prover model, and we realized that the multiple prover model is equivalent to something called I have to say, one thing, I was good at theorems. I wasn't great at naming things. So we had called this the Oracle proof system. But later on, it got a better name, probabilistic checkable proofs. I'm not sure who came up with that name, but it's certainly better than what we had. And the idea of a probabilistic checkable proof system is instead of a proof which is interactive, where you ask me questions, I give answers, you ask me questions, I give answers, I'll write down the answers to all the questions ahead of time, and I'll publish it in a big library. So it's an exponentially large library, but I write down all the questions, I write down the answers to all the possible questions, and then I leave the room. So I can't change them afterwards. And what we showed is that what you could do with multiple provers was equivalent to what you could do with these probabilistic checkable proof systems. Everything you could do in this model, you could do with the multi-prover model. And the difference between this and a regular interactive proof system is in a regular interactive proof system, you can change your answers based on the previous questions that were asked. In a probabilistic checkable proof system, all the questions had to be answered ahead of time. That turned out to have a lot of power, and it turned out to be very similar to the multiple provers. And the basic reason was you basically use one prover, yet you use the provers to check that the answers were consistent, that these answers were basically chosen ahead of time. We claimed in our paper that we could actually do this with only a constant number of rounds with the protocol. The idea is that somehow we can get some small amount of error and then repeat it many, many times, and the error would go down. It turned out that we just kind of made this statement that clearly you can see the error goes down exponentially when we repeat this thing in parallel. It turned out that clearly required a 30-page proof by Ron Raz that would be later known as the power law repetition theorem. But it does turn out, although not as trivial as we thought, that if we repeat this protocol over and over again, that the probability drops down. So that's this probabilistic checkable proofs. And then we get on to 1989, fall of the Berlin Wall, people historical principles. And then we started, and 1989 is where, all these things, all these kinds of results were sort of interesting, but they were all kind of the prelude. 1989, I graduated from MIT. What happened was, in 86, Mike Sipser moved from Berkeley to MIT, and I followed him. So that's how I was at MIT. 1989, I graduated, personally, I got my PhD at MIT. I moved to University of Chicago, where actually I started on a 2-year assistant professor position. But what was happening research-wise was papers that didn't look initially related to interactive proofs at all. There was a paper by, 2 papers, and I actually can't find them online, so I'll just kind of give the titles here. One is by Don Beaver and Joan Fagamam, called Hide Instances of Multi-Oracle Queries, and by Dick Lipton, New Directions in Testing. And what do these papers talk about? So they didn't talk about interactive proofs. So what did they talk about? Well, hiding instances of multi-oracle queries. The idea is that the question is, I want to be able to ask questions to a database. It's almost like a privacy question. I want to ask questions to a database. I want to get the answers, but I don't want the database to know what questions I'm asking, which sounds a little strange. But it turned out you could do this if you had many databases. You could do this for certain kinds of questions if you had a lot of databases. And basically, they were looking at what kinds of questions you could ask Beaver and Feigenbaum that you could answer with these different databases and not have them know which question you were asking. And one example they gave was if you had a low-degree polynomial, then there were some tricks where you could ask different questions to each database so that each database basically got a random example, and then you could interpolate and then find out what the problem you really wanted to solve, even though every database you asked that looked individually random. I mean, they were not uncorrelated, not independent, but the questions individually looked random to each database. And then Dick Lipton looked at what was called the permanent function and basically realized it was a low-degree polynomial, and so you could apply the permanent function. You could show, if you wanted to know the answer to a permanent function, you could ask queries lots of different databases, and no database would know what question you were asking because it looked completely random, which permanent you were particularly interested in, but you could still compute the permanent of a specific instance. What's the permanent? So just consider a matrix. The determinant of a matrix is, so mostly you've heard about the determinant of a matrix. Determinant of matrix is, well, I don't know how to provide determinant of matrix, but it's basically, if you wrote down the formula for determinant of matrix, it looks like this. It's the sum of, you take every possible way of taking a number from one row and a different column for the second row, a different column for the third row. You take all the possibilities, you sum them up for every possibility, and then you throw in this -1 factor for whether the permutation from rows to columns is odd or even, and then this gives the determinant. The determinant is something that's critical for, like, determinant is 0 if the matrix is non-singular, and it's relatively easy to use to compute the determinant using Gaussian elimination or some various other ways. You can use the determinant to compute inverses. It's a very powerful tool. So the determinant in particular, it's easy to compute. Now, what's the permanent of a matrix? It's basically the same formula except to get rid of this -1 term. So it's even a simpler formula. You just sum up, you just take the product over, for every permutation, you take the product of xi sigma I, and you sum all those up. And you think with a simpler formula, it should be even easier to compute. That turns out to be not the case at all. The permanent turns out to be as hard. There's a paper by Valiant that shows the permanent is as hard as any counting problem, counting number of 3 colorings of a graph, counting the number of satisfying assignments to a formula. The permanent turns out to be incredibly complex. But the permanent is a low-degree polynomial. That's the low-degree polynomial. I mean, over many variables, but that doesn't, it didn't turn out. So the permanent is this problem where it's really interesting, and yet you could use it to, you can use it to ask different queries to different oracles, different databases, and no database knows which particular matrix you started with. So that was that's what those two papers did. But that led to so this paper, Algebraic Methods for Interactive Proof Systems. Now this really started with Noam Neeson. So I mean, it kind of was one paper in the end. But Noam Neeson realized if you take any problem that has this randomness property and this downward, what's called the downward self-reducibility property, basically if you take the permanents, you can reduce the permanent to smaller instances by, I won't get into it. You can take a permanent of n by n and reduce it to questions of n by n, n minus 1 by n minus 1 by basically crossing out a row and a column and computing that permanent. And if you do it in the right way, you can compute n by n permanent from n minus 1 by n minus 1 permanent. So if it has a downward self-reducibility property and this randomization property, then you could do it with, then you basically take the permanent, all the permanents, and you can create a probabilistically checkable proof, a large one, for the permanent function. That's what Noam Neeson did. And then Noam Neeson, and this is where, this is also 1989, so I'm thinking this technologically. What started happening in the late 80s, so email. You think about email. I mean, email was there since, I think, started to be popularly used in the early 80s. So in fact, in the early 80s, I worked for computer services at Cornell. That's where I did my undergrad. and actually worked on this project for several years, writing an email system in assembly language. It was really an interesting project. And I got to learn a lot about email. And email there was in its infancy. People sent each other short messages. It was slow. Not everyone had email accounts. And then gradually, towards the end of the 80s, people started to all have email and started to use email for communications. But it wasn't until sort of the late 80s that we really used email to send papers around. So before then, if you wanted to send a paper to somebody else, if you wanted to see someone else to see your research, either they'd have to wait for the conference proceedings and somehow get a copy of the conference proceedings, from the library, or if they actually went to the conference, or they would ask you for the paper, and then you would mail it to them. You had these like tech reports. So basically, you took the front office of the department would have a paper. They would slap a cover on it, and if people requested it, you'd send out lists of papers. If people requested a paper, they would staple it together and stick it in a mailbox. Sometimes we would even get these stamped self-addressed envelopes from places asking for copies of our papers. And so that's how we distributed papers, say in the mid-'80s. I mean, when you submitted papers to conferences, you actually stuck them in an envelope and FedExed them to the conference. I mean, those were the early days. Now, in the late 80s, though, we learned how to email papers. Generally, you emailed like LaTeX files or PostScript files to other people. Now, we didn't have attachments back then, so you just stuck the paper in the file. Sometimes that caused some funny things. If you look back at old papers, sometimes I don't know if you've ever seen an old paper where there's like the word "from" has an upside down question mark before it. So does anyone know why that happens? Oh no, that's someone young. Yeah, it's some of the old people. So what happened is the mail program, if it saw the word "from," it didn't want "from" to be confused with the real "from" line. So it put a greater than sign before the "from" to distinguish it from a real "from." And then the greater than sign is interpreted by LaTeX as a Spanish upside down question mark. So that's why you would get this upside down question mark before the "froms." Just an interesting story. And then, so when you wrote LaTeX, you put the word "from" in brackets or something to prevent this from happening. Once you had attachments, this all went away. So why am I telling you all these stories about the early days of email and files? Because what happened was Noam Nissan, and I didn't really see this before, mass mailed this paper to, 30 or so people around the world. Luckily, I knew Noam because we'd started grad school in the same year at Berkeley. And then he actually came and did a postdoc at MIT, so we overlapped a year there. So I was on Noam's distribution list. And I get this pair from Noam, and I asked him, well, you did this for multiple provers, for publicly checkable proofs. Can you do it for a single prover? Noam said, I don't think so, and he gave a reason, and the reason didn't make a lot of sense. So we started looking at this. I started working with Howard Koloff, who was actually an algorithms person, and Karsten Lund, who was a student that I had picked up at University of Chicago when his advisor didn't get tenure. This is the best way, by the way. Show up at a university when starting your academic career, pick up a student who's already been trained. Because their advisor was forced to leave. So anyway, Karsten and me and Howard started playing with this and trying to see, can we get this two-player prover protocol to work with one prover? And then one day, Karsten walks into my office and says, why doesn't this work? I love that attitude. But it did work. And then that gave us a single prover protocol to convince you about the value of the permanent. And remember what Valiant showed, that the permanent could give you any counting function. So in particular, you could show that the number of solutions was 0. I could convince you the number of solutions of a problem was 0. What does that mean? I could convince you there are no solutions. I could convince you that a problem isn't satisfiable. I can convince you that there's no three coloring of a problem. I could convince you that things aren't possible. It was kind of a, when you look back at it, it's kind of surprising. I mean, I talked about my own results, so I probably shouldn't brag too much. But I found this really exciting. This is really exciting that you could convince someone that something isn't true. And then I took that result. I wrote it up. We asked Noam, listen, your paper hasn't been out that long. We've improved it. We obviously used a lot. We wouldn't have done this without your paper. So let's merge. So we merged the two papers, and then I wrote it up. Basically wrote it up, and then I emailed it to a whole big distribution list. This has turned out to be, retrospect, a little controversial. Obviously, who gets to see these papers, and who didn't get to see the papers because I just didn't happen to think of adding them to this distribution list. And now we've gotten away from this because, later on I would put all the papers on my website, and then after that, now we have these archive sites, and basically papers are published for all to see, so I'm glad we got past that. But back then, it almost was a lot of who you knew. But there really wasn't the technology to get around that back then. And then there's a nice paper by Laszlo Babai. He wrote a paper called Email and the Unexpected Power of Interaction. It talks about how these email issues happened and how different communities were cut off from it, and it was an interesting perspective at the time. So I could convince you that the graph's not three-colorable. Okay, then what happened? So then we sent the paper, I said, to lots of people, and then one of those, and this was sort of December of '89. We had tried to push it. So we had shown that interactive proofs could do all of Cohen P using something called Toda's theorem. You get the entire polynomial time hierarchy, but it wasn't known whether you could get p-space. P-space mean everything you could solve in polynomial amount of memory. Now we knew the upper bounds of interactive proofs were contained in p-space. That goes back to I forgot who Feldman proved that theorem. So that actually that everything in interactive proofs you could do in p-space, but we didn't know that gap, and we weren't sure you could get all p-space. Our proof kind of fell apart because when you converted what we tried to do to alternation, you had these multiplications, and it was no longer a low-degree polynomial. So our proofs fell apart. Adi Shamir figured it out. Turns out that if you look at the proof that shows that p-space equals alternating polynomial time, a result of Shannon, Coase, and Stockmeyer, the way that proof works, the degrees don't get very high. And so you could use that proof to get IP equals. And he was actually able to show that p-space was in IP. So that's Adi Shamir. And then later on there was a paper by Alexander Shen who found a way to do it just by saying, well, if the degree gets too high, just reduce it. Just doing a reduction operator, and that turned out to work as well. So there are a couple different ways you could get IP equals p-space, get the equality from this paper. I know this all happened kind of at the end of December. The U.S. kind of shuts down at the end of December, so I think I went away on vacation. Babai got angry at me. How could I go on vacation while the Israelis were still working and solving these problems and extending our results? Well, us Americans on vacation, that's just the way life works. Adi didn't want to merge with us, so we ended up publishing two different papers, which doesn't bother me, except it does, I have to be honest, still bothers me sometimes when you see it written out as Shamir's theorem, IP equals p-space. Still still need to see that this was actually all sort of solved. And you can actually convince someone. So, NP you think of as graph coloring, P space you think of as chess, and basically what you can do when you get back and forth interaction as much as you can. So let's move to 1990. So it turned out that IP equals P space is not the end of the story, because you still had these two provers. What happens when you have these multiple provers? And there, the upper bound we had, which we'd shown in the Fortnow paper, was something beyond P space called non-deterministic exponential time. Everything you can prove to someone who can verify things in exponential time. Turned out to be quite a step above P space. And then, working with Laszlo Babai and Karsten Lund, Laszlo Babai was also at University of Chicago, we had managed to show that everything you could do in non-deterministic exponential time you could actually do with only two provers, or in this probabilistically checkable model, that you could actually get non-deterministic time. The idea was basically, the way we did our proof was basically you had to get a low degree polynomial. Basically what you did was you took this idea that you can express non-deterministic exponential time as an exponentially long proof with an easy checkable, which you could easily check whether the proof, you could check whether, there's local checks, and if all the local checks held, then the proof was valid. And then, so you tried to push this into the Cohen P. You basically had the probabilistically checkable proof was basically this proof, and then you do an interactive proof for the check, and then that didn't work because things weren't a low degree polynomial, so you made everything a low degree polynomial, and that still didn't work because the prover could cheat and not make it a low degree polynomial, so you had to do some sort of low degree test, and that's what took a lot of the work, and we came up with this crazy proof, and it's gotten a lot simpler over time. But that's how that worked for us. And then that's kind of where I felt the story ended. I said, wow, we've interacted IP equals P space. We have MIP equals next. Multiple interactive provers give you non-deterministic exponential time. We now know everything we want to know about interactive proofs. I'll go do something else. That's kind of how I felt. And this turned out to be a mistake for me because it kept going. And it kept going in kind of a surprising way. It kept going because of this paper by Feige, Goldwasser, Lovaas, Safra, and Segedy, FGLSS, interactive proofs and the hardness of approximating cliques. So what's the clique problem? The clique problem is, it's an old slide. You recognize the characters. You probably don't because it's an old slide. But the clique problem is, if I have a group of people, some of which are friends, a clique is a bunch of people, say these 4 people, all of whom are friends with each other. And then the question is, like say in Facebook, is there a group of 200 people, all friends with each other in Facebook? That's an NP-complete problem in general. But can you even approximate it? Can you even find something that's close to the right size? And then Feige, Goldwasser, Lovaas, Safra, and Segedy looked at this MIP equal next result and realized you can convert it to say something that, well, you can't approximate clique unless P equals NP in various ways. I won't give you the exact parameters. But they basically showed you can't really approximate clique well at all. And this is kind of a shock, because it took our paper, which was purely a complexity result, and converted it to an algorithms result. It said there's no algorithm for approximating clique unless you could solve it exactly. Which was kind of a big, you didn't see that a lot. We took a complexity result and turned it into kind of a question about algorithms. And so algorithms people got interested in our work. And then, and that led to a paper by Aurora and Safra, and then this very famous paper, what's called the Pcp Theorem. So the paper was called Proof Verification of Hardness of Approximation Problems. And this is Aurora, Lund, Mott, Wani, Sudan, and Segedy. But it's best known as the Pcp Theorem. And basically what it says is you can take any problem in NP and convert it to a problem where you can be convinced of the proof by asking random questions. We only have to look at a constant number of bits of the proof. In fact, you can get away with 3. You can look at 3 bits of the proof, and you only have to use that many coins, order log n coins. So you have order log n bits of randomness, You only need to look at 3 bits of the proof, and then you will be convinced with some reasonable probability that the proof is correct. 3 bits. That's it, not 3 numbers, not 3 bits. That's all you have to ask to the proof. And but the point is not that you could do this 3-bit thing. The point is they did this because these are the parameters that help you do tight approximations. And so this led to a Pcp theorem, which showed a whole class of problems were very hard to approximate. And then this led to a whole series of papers, which are still continuing today, about variations on proofs, on different various parameters, and how it applies to different approximations. A lot of theorems that are still going on. So, I was a little bit ahead of my schedule, but so I'll talk a little bit about these things. There's more that came from this line of work. I can't really cover everything. This notion of program checking. So the idea is, I want to give you, you have the output of a computer program, but you don't know whether it's computed the right thing. You don't want to simulate the entire program. Is there a way to check it with only checking a few parts of the program? And you can take this multi-prover interactive proof system and convert it into sort of an extra information that you can use for program checking. It was a very theoretical result at the time. It wasn't even, in fact, entirely correct in our paper. It needed some fixing up. But now you're actually starting to see people take ideas from this paper and actually implement it, and that's kind of neat. This is the idea of Subhash Coates, what would be called the unique games conjecture. This is kind of a strengthening of the Pcp theorem. It's still open whether you can get, it's basically a stronger version of PCPs. And I won't get into the exact definition. But basically what Subhash Coates realized that if this unique game is conjecture is true, you could get a lot tighter approximations for various approximation problems. Probably the best example is vertex cover. Vertex cover, I give you a graph. How many vertices do I need to cover all the edges? There's an easy algorithm now to get you an approximation factor of 2. The Pcp theorem shows the lower bound is, I forget exactly what it is, 1 point something. And if unique games conjecture was 2, you would actually 2 would be the lower bound as well. So you get tight bounds for things like that problem and lots of other problems out there as well. And so there's been a lot of work on unique games conjecture. There's some various partial theorems. I think it's still an open question whether or not unique games conjecture is true. I mean, it could be the case where the unique games problem is not quite NP complete, but somewhere between P and NP. But it's still open. And then there's this interesting question about multiple proof or interactive proofs where the provers can't communicate, but they start off with entangled quantum bits. Now, entangled quantum bits allow communication. You can't communicate with entangled quantum bits, but quantum is weird. Let's face it that way. So if I measure the bits in a certain way, they will measure out the same way. So you can't use it to communicate. I mean, there's various theorems that show that quantumness, it'll look the same distribution no matter how you measure it, but still entanglement could somehow be used. And it was a big question for a long time whether having this quantum entanglement changed the power of multiple provers. With multiple provers, I mean, maybe it's weaker, maybe it's stronger, maybe it's the same, maybe it's irrelevant. Because maybe they could cheat if they had quantum provers, or maybe they could make them even more powerful because they could do more things. And it turns out the answer is it's more powerful. So this paper, which is now just 6 months old by Natarajan and Wright, showed that non-deterministic double exponential time can be done with multiple provers who have quantum entangled bits. So that's an exponential higher than what we had before. NP is what you get if you have a prover who can just send information to you and you check the proof and no randomness. Non-deterministic exponential time you get with these multiple provers or PCPs without any quantumness. And non-deterministic double exponential time is what you get with quantum. And I shouldn't say there we don't know the upper bounds. So we don't even know if it's computable. It could be even much more stronger than non-deterministic double exponential time, but that's what Natarajan and Wright showed. And I want to get back to this death of proof. I'm going to kind of end here. So what happened here? So there was this writer, can't see his name, John Horgan, and he looked at a lot of results around that time, 1993. And there was our stuff on program checking and interactive proofs, but there were also, this wasn't long after, say, the proof of the four-color theorem, which was done with this computer checking lots of examples. And then there were various other kinds of work where you had done a lot of simulations or various other things. And so John Horgan was saying, well, the proof as we know it is dead. Is that we don't do these mathematical logical proofs anymore. We do these proofs where people are convinced, maybe not entirely, they're convinced, maybe not entirely 100%, but in these statistical senses, like we did with interactive proofs. So what's this say? Computers are transforming the way mathematicians discover, prove, and communicate ideas, but is there a place for absolute certainty in this brave new world? Yeah. So anyway, it went on this. Now it did talk about this guy doing this old-fashioned proof, a guy known as Wiles, Andrew Wiles, who showed that, and this happened like right around the same time, Andrew Wiles showed that Fermat's last theorem was true. Some of us are old enough to remember Fermat's last theorem was just a conjecture. Fermat claimed it, but no one had actually seen a proof. And everyone who was a kid at the time who was a math nerd, so me and Andrew Wiles and probably everyone else at the time, just dreamt of solving Fermat's last theorem. It was a great problem because you could state it. It's pretty easy to state. I wonder if you guys, can you young ones state it? Yeah. So you could state it, x to the a plus x to the b. Wait. I can't even state it. X to the a plus y to the a equals c to the a will only work for integers if a is 1 or 2. It won't work for integers when a is at most 2. Otherwise, there are no integral solutions other than some trivial ones like things being 0. So Andrew Wiles actually, after a long series of papers, actually settled this problem. And this paper called it an anachronism. This was the old-fashioned proofs that occasionally still happen. And you can see the mathematicians were up in arms, and of course, unlike our proofs about interactive proofs were formal logical proofs. There was still obviously a lot of, and of course, everything we do in theoretical computer science focuses around real proofs, not to mention everything mathematicians always do. So I think a lot of time people. At the time, people were, really upset about this paper. But, looking back at this, think about this sentence today. Computers are transforming away I wouldn't say mathematicians. Let me take out the word mathematicians. But computers are transforming away. People discover, prove, and communicate ideas. And is there a place for absolute certainty in this brave new world? And think of it applied to things like machine learning. Machine learning, which learns things and does an extremely good job, better than, in many cases, better than we can do using kind of more traditional programming ideas. But we don't know. It's not absolutely certain. It's always going to make mistakes because it's learning from distributions. And we don't understand why it's working. But we still use it to understand things, to communicate things, and do things. And in general, just the way society views things today, I think we're moving away from times when people are requiring proofs of ideas. People want to see things for what, people have these beliefs and they want to understand their beliefs, but they move away from sort of formal logical reasoning, or if they do formal logical reasoning, they do it with various different assumptions. So while the death of proof, I think, maybe didn't make sense in '93, it's something we should think about today. And but I think we're much more willing today, maybe not this audience, but I think society is much more willing today. I mean, if I give you the trade-off, and there's often a trade-off between a machine and the quality of a machine learning algorithm and how much we understand what it does and how much we can prove what it does, a lot of people will take the accuracy and will trust the machine learning algorithm and not worry so much about what we can prove about it. You look at the emphasis, you look at the machine learning, there's machine learning theory and there's machine learning practice, and there are people who are trying to mesh the two together. But the theory is way behind the practice. And a lot of the people in practice don't even worry so much about the theory. So it's really, it's not that these weren't issues back 20, 30 years ago. I just feel like there's definitely a different mindset, a different change these days. So, yeah, that's sort of what generated John Horgan's article in the first place. This proofs that they're very long that only can check by checking. Like the best example is the 4 color theorems. Every planar graph is 4 colorable. That you had to have a computer check all the possible cases. Packing, yeah, probably even more complicated. Anyway, this is just honest thought. I like to end this. I'm a little early, but I don't think anyone's going to complain. So thanks very much for giving me this time.